Hello and namaste everyone. Welcome to lecture 4. So, let us do a quick recap of what we have covered so far. In the previous 3 lectures, we have looked at an introduction to stochastic approximation. I gave you this general abstract form of how a stochastic approximation algorithm looks like. Thereafter, I gave you 2 examples of stochastic approximation methods. In the first example, we looked at estimating the expected value of x using independent and identically distributed samples of the random vector x itself. In the second example, the problem broadly was looking at estimating the expected value of x using samples of a related random variable y, right. We later saw that both these methods were examples of SGD methods. However, as I have repeatedly mentioned, the true potential of stochastic approximation methods is that they can generalize beyond SGD. This feature makes it really popular in application areas such as reinforcement learning. Often I will abbreviate reinforcement learning as RL. So in this lecture and the next, we will look at an example of a stochastic approximation method which is not an SGD, that is, it is not a stochastic gradient descent. At a very broad level, this example involves what is called as policy evaluation in reinforcement learning. So that the students and the audience can get a better understanding of this problem, I am now going to give a very brief introduction to reinforcement learning. So what is the philosophy of reinforcement learning? Well, it looks at how does one learn to play interactive games such as chess. So how do you do that? Well, you play the game multiple times starting with an arbitrary strategy and then continually improving upon it. I think there is a typo in the word continually, it should be continually, right. So RL aims to extend this trial and error philosophy to help autonomous agents control an interactive system so that some long term objective is maximized. Let me elaborate what do I mean by that. Formally, this interactive environment in reinforcement learning is represented by a tuple made up of 5 things. It is S, A, P, R and gamma. So what do these 5 things represent? Well, S is the state space, that is the different possibilities for the environment. For example, in the context of chess, the configuration of pieces will decide what the state of the game is. A represents the action space. This is the the set of actions that is available to the autonomous agents. P is referred to as the transition kernel. I will describe to you what is P in the next slide. R is the reward function and gamma is the discount factor. Again, I will talk about what R and gamma mean in the subsequent slides. Okay. So what is this transition kernel? The transition kernel P is actually a function. So for a function, I need to specify what is the domain and the range. The domain of this function P is the Cartesian product S, which is the state space, cross A, which is the action space, and the range of this function P is delta of S. Delta of S is the set of distributions on the state space S. Now throughout our discussions, we will want to discuss things in a simplified fashion. For that reason, we will presume throughout that S, the state space, and A, the action space, are finite. In that case, this transition kernel P is characterized by the set of values P S prime given S comma A, where S and S prime come from the state space S and A, which is the action, comes from the action space A. The value P S prime given S comma A specifies the probability of the environment transitioning to a state S prime from a state S under action A. So you can think of you playing the game of chess against a computer, right. So the current state, which is S, is the current configuration of pieces. The action is the move that you make, right, and then the computer looks at the move that you have made and makes a different move, right. The move that you made is A over here, right, and after the computer makes its move, the configuration of pieces will change and the new configuration of pieces is S prime, right. Now here P of S prime given S comma A specifies this random transition, right. Now when you are playing against a computer, right, you can imagine that you are at a state S, you played an action A, right, and the computer changed this configuration to S prime in some random fashion, right. So this is what is captured by this function P, or this set of values P of S prime given S comma A. So that captures the definition of this quantity P, right. Next we move on to the reward function. The reward function is denoted by this function R. The domain of this function again is the Cartesian product between the state space and the action space, and the range of this function is R, which is the set of real numbers. Now this function, which is R, specifies the immediate reward that the agent gets when the environment is in state S and an action A is taken. I will elaborate a bit more about this soon, right. And finally the discount factor gamma, right, this is a scalar value which lies between the interval 0 comma 1. So it is closed at 0 and open at 1. So we will not allow gamma to take the value 1. Now this discount factor gamma specifies the relative value at time t of the reward that you obtain at time step t plus 1, right. So the intuition over here is as follows. Imagine someone promised to give you 1 rupee today, so it will have some value for you today. So let us try to understand the notion of a discount factor. The idea is the following. Suppose someone promised to give you 1 rupee today, it will have some value, right. Now imagine someone promised to give you 1 rupee after 1 year. Now what value will this 1 rupee that you will get after 1 year today, right, what value this 1 rupee that you will get after 1 year will have for you today, that you can already see will have different values, and this difference in some sense is captured by this discount factor, right. So with this understanding of these 5 different things, let us see how an interaction episode between the agent and the environment may unfold, right. The environment's initial state could be S0, right, and then the agent takes an action A0, right. So the agent environment is in state S0. So in the context of chess you can imagine some initial configuration of pieces, and then you as an agent take an action A0, right. Now as soon as you take the action A0, or the agent takes an action A0, the agent gets an immediate reward specified by R of S0 comma A0. So you can see that this reward is a function of S0, which is the initial state, and A0, which is the action that you took, right. And after the agent gets this reward, the environment transitions to a new state S1, right, and this new state S1 is sampled from the distribution which is specified by P of S given S0 comma A0, where S lies in this state space S, right. So let us try to understand what do I mean over here. So notice that you started at S0 A0, right. So that is present over here. Now what is the next state? So first we need to understand that this next state is actually a random state, right? So which means there is some probability of moving to, you know, the first state, there is some probability of moving to the second state, and so on and so forth. So which quantity describes these probabilities? Well, it is specified by this P, right? And since we start at S0 A0, so that is fixed. The next state is the random variable, right? And P of S given S0 comma A0 specifies what's the probability that starting from S0 A0 you move to a specific state S. So from this distribution you sample a state, and whatever state you get you represent it by S1, right? Now later on the agent sees this state S1 and takes this action A1, right? And from this point on the sequence of steps repeat. So what do I mean by that? You are at S1, you took this action A1, so you will now get a reward which is a function of S1 and A1, and because you have taken this action A1, the environment will now make a transition to a new state S2, which is specified or which is sampled from the distribution P of S given S1 comma A1, right? Alright. So as a trajectory, this interaction, right, can be viewed as some evolution in the following way. That is, you start at state S0, the agent takes an action A0, then you get a immediate reward R of S0 comma A0, and the environment makes a jump to some random state S1. At this point in time the agent takes an action A1 and it gets a reward of R of S1 comma A1, where ST plus 1 for any t comes from this distribution P of dot given ST comma AT. So the dot here is to be represented as a variable, or alternatively you can think of this as coming from the distribution P of S given ST AT, where S comes from the state space S, capital S, right. So once you are at ST AT, the next state is sampled from this distribution, then you move to ST plus 1, then you pick action AT plus 1. Once you have ST plus 1 and AT plus 1, again the environment first gives you a reward and then makes a transition to ST plus 2, and so on and so forth, right. The goal of the reinforcement learning agent then is to find the sequence of actions A0, A1, A2, A3 and so on, such that this expectation is maximized. Okay, so let us look at this expectation. First of all, this expectation involves an infinite sum, right. So the index of this infinite sum is t, which denotes time, and it starts from 0 and goes all the way up till infinity, right. And R st comma at specifies the reward that you get at time step t, right. So R st comma at is the reward that you get at time step t, and this gamma to the power t is multiplying it. This denotes the value that this reward that you obtain at time step t you have at time step 0. Okay, so you have some relative quantification of how good that reward that you will get at time step t holds for you at time step 0. Okay, that is why you multiply by gamma to the power t, and one can see that since gamma is strictly less than 1, as t increases the value of gamma to the power t decreases, right. So which means that the reward that you get far away into the future has less importance to you today compared to the reward that you will get in some nearby time instance, right. So you look at this infinite sum, right. So this infinite sum, because the states are randomly evolving, this infinite sum will be a random variable, right, and hence we look at its expectation, which makes sense, which will be now a real number, right. And this expectation has some conditioning which specifies from which state do you start, right. So let's go over it one more time. You start at this state S, right, and then you take this action A0, then you move to S1, right. So at that point in time you will get this reward R S0 comma A0, right. Then you move to state S1, right, and then you take this action A1. So at that point in time you will get this reward R of S1 comma A1. Then you move to state S2, by you I mean the environment moves to state S2, and you as an agent take this action A2 and you will get this reward R of S2 comma A2, and what value this reward that you will get at time step 2 relatively holds for you at time step 0, right. So this is gamma square S2 comma A2 and so on. Is this okay? So you can see that this infinite sum is described in this fashion, right, and this sum is random because the states that you observe are random, right. And the goal of the RL agent is to find the sequence of actions so that the expected value of this cumulative sum, expected value of this cumulative sum of discounted rewards starting from the state S is maximized. Okay, so this is the goal of the RL agent, right. So we can state this more formally. Suppose you have a policy or a strategy pi, right. So I am introducing this formal description for the first time, right. So here the agent took this action A0, A1 and so on, but how does the agent decide which action to take? That is described by the agent's strategy, and we will formally denote this by the symbol pi. Now what is pi? Pi is a function, right, its domain is the state space and the range is the action space, right. So an agent strategy you can view it in the following way, that the environment is in a state S, right, and little s, and pi of S specifies the action that the agent prefers to take, right. Similarly, if the environment is in state S prime, then pi of S prime specifies the action that the agent plans to take, right, and so on and so forth. Okay. So now given agent's strategy or policy, so I will interchangeably use this word strategy and policy. Now given agent strategy, its quality is measured via a vector which we denote by V superscript pi. Okay, so once in a while I will also denote it by V subscript pi. So this vector is a vector of size, I should maybe emphasize that it is the vector of size cardinality of the state space S, right. So if you have two possible states, then V pi will be a vector of size 2, it will be a vector in R2. If similarly if the cardinality of the state space is 100, 1 billion, 1 trillion, then V pi will be a vector of corresponding dimension, right. So given strategy or policy of an agent which we denote by pi, its quality, right, its quality is quantified by a vector which we denote by V pi, and we call this vector as the value function, right. Now what is the sth coordinate of this vector V pi? Well, the sth coordinate of this vector V pi is given by this expectation, right. So let us go over this expectation and see how this differs from what we saw before. You see this S over here, right, you see this S over here, this S prescribes the starting state, right, this S prescribes the starting state. So the sth coordinate of V pi means that you start from state S, right, and thereafter pick your actions prescribed by your policy pi. So what do I mean by that? So you start from S, right. Now since you are at state S, pi specifies an action pi of S, right. Now since this action is specified, you will get a reward r of s comma pi of s, and then you will make a transition to the state S1. By you again I mean the environment makes a transition to the state S1. Now at S1 the agent again decides to take the action pi of S1. Recall that pi is a function from the state space to the action space. So pi of S, pi of S1 and so on and so forth, they are actions. So as soon as the agent takes this action, it will get the reward r of S1 comma pi of S1, right, and so on and so forth, right. So again we can look at the sum of rewards. So maybe I will write it over here. So we will look at the sum of rewards r of S0 comma pi of S0 plus gamma times r of S1 comma pi of S1 plus gamma square r of S2 pi of S2 and so on and so forth, right. So again we can see that you have a cumulative sum of discounted rewards, right. Again this sum is random because the evolution of the states is random, and it is random because the environment evolves randomly, which is as prescribed by this transition function p. So this infinite sum is random, and we are interested in looking at the expected value of this, right. So what is v pi of s? Well, it is the expected value of this cumulative sum of discounted rewards. The difference between this infinite sum and what we saw before was that previously it were some arbitrary sequence of actions. However, in this case the sequence of actions are as prescribed by this policy pi, right. So that is why this left hand side is v pi of s. Now what is the goal of reinforcement learning? Well, the goal in reinforcement learning is to find a policy pi star such that v pi star of s is greater than equal to v pi of s for all policies pi and all states little s, right. So in words, the goal of reinforcement learning can be said to be to find a strategy or a policy pi star. So what does a strategy or a policy specify? It specifies which actions to take at which states, right. So you can imagine that when you are playing chess, you look at a configuration of pieces, you say okay, I will take this action. You look at a different configuration of pieces which corresponds to a different state of the environment, you say okay, I will take this action now, right. So you come up with a strategy which says at this configuration of pieces you will take this action, at a different configuration of pieces you will take this action, and so on and so forth. And you can see that this mapping from the configuration of pieces which specifies the state space and the action space corresponds to your strategy, right. And the goal in reinforcement learning is to find a strategy or a policy pi star which gives you the largest returns, right. By returns I mean this expected sum of discounted cumulative rewards, right. So you can think of you play this game forever, right, and you are looking at the rewards that you get, and you would like to get the maximum sum of these rewards, right. And in that way pi star is the policy such that v pi star of s is bigger than v pi of s, right. And notice that we require that pi star be better than pi for any starting state s. Is this okay? So with this we come to the end of the lecture. Now I will be summarizing what we have done in this class. So as I said in the previous lectures, we looked at examples of stochastic approximation, but they were SGD methods in disguise. In this lecture and the next, we want to look at an example of stochastic approximation which is not a SGD method. Towards that, I gave you a basic introduction to reinforcement learning and tried explaining to you what the goal of reinforcement learning is. In particular, I told you what the value function of a strategy or a policy pi is, right, and I told you the goal in reinforcement learning is to find the strategy which has in some sense the largest value function, right. And one of the intermediate goals in reinforcement learning is what is called as policy evaluation, which basically refers to the problem of finding v pi given pi, right. And we will discuss an algorithm called as the temporal difference learning algorithm in the next lecture to estimate this v pi vector, right. And you will see that the TD0 the temporal difference learning algorithm that we will discuss cannot be expressed as an SGD, and hence in that sense that is an example of a stochastic approximation algorithm that is not an SGD. With this let me stop lecture 4. Thank you and namaste.